Welcome to Pre-Calculus Trig, Section 3.1 on simplifying with fundamental trig identities. The fundamental trig identities that we're going to be using to simplify trig expressions are the ones that we've already used before. So the tangent is the sine over the cosine, the cotangent is the reciprocal of the tangent or the cosine over the sine, the cosecant is the reciprocal of the sine, and the secant is the reciprocal of the cosine. The other fundamental identities which we're going to use in this section are the Pythagorean identities. So I'm going to briefly go over how we developed these back when we started talking about the unit circle. So this is a sketch of the unit circle, which is a circle of radius 1 centered at the origin. So any angle theta can be represented with the initial side on the positive x-axis and the terminal side here, and that terminal side indicates that I've rotated through this amount theta from the initial to the terminal side. So if I drop a perpendicular from this point here down to the x-axis, I can form a right triangle. So it'll have an x distance here as the side length there, which is the adjacent side to the angle theta. And then I'll have a y distance here, which is the opposite side to the angle theta, if we're considering that theta is our reference angle. So now we can say that x squared plus y squared is equal to 1 squared, and 1 squared is just 1. Okay, so that's the Pythagorean theorem for that triangle. Next, we can say that the sine of the angle theta is equal to the opposite side over the hypotenuse. So in that triangle there, the sine of theta is equal to y over 1. So the sine of theta is equal to y. So now let's talk about the cosine. So we can say that the cosine of theta is equal to the adjacent side over the hypotenuse. So that means the cosine of theta is equal to x over 1, or the cosine of theta is equal to x. Now we can substitute for x and y in this equation, and we'll get, substituting for x, the cosine of theta squared plus the sine of theta squared is equal to 1. And looking at this note down here, the exponent is typically written between the trig function and the variable like this. And so this is this type of notation here. Sometimes you'll see it written like this here, where the parentheses must be written around the entire thing and then squared on the outside, but generally not. This is not very common. You'll usually see it like this. So if we write it that way, we've got the cosine squared of theta plus the sine squared of theta is equal to 1, and you could also have it written this way. It doesn't matter either order. So we've developed this first identity. Now let's work on the next one. So if we have the sine squared of theta plus the cosine squared of theta is equal to 1, and I divide through on all three terms by the same thing, sine squared of theta, I'll get 1 here, and then on the second one I'll have the cosine divided by the sine, and that whole quantity squared. So that's equal to the cotangent squared of theta. And then on this last one, I've got the reciprocal of the sine squared of theta, which would be the cosecant squared of theta. So we've developed the second Pythagorean identity. Now for the third. So starting with sine squared of theta plus the cosine squared of theta is equal to 1. This time I'm going to divide through by the cosine squared of theta to get an alternate form of the Pythagorean identity. So now in the first term here, I've got the tangent squared of theta, because sine over the cosine is the tangent. So this is the tangent squared of theta. And then we have 1 for the second term now. And then this last term here, 1 over the cosine squared, that's equal to the secant squared. So we've developed the third version of the Pythagorean identities, and these are all related. So we're going to use the identities to develop methods for simplifying trigonometric expressions. So example 1 says simplify the products to a single trig function or a constant. So we don't want any fractions in our final answer. So we're going to do some substitutions. So we know that the cosecant of x is 1 over the sine of x. And this is a product, so I'm going to put a dot here. So we know the tangent of x is equal to the sine of x over the cosine of x. So this is equal to the sine of x divided by the sine of x times the cosine of x. So I can go ahead and cancel out the sines, and I'll be left with 1 over the cosine of x, which we know is equal to the secant of x. So this is our simplified form of the given product. So for part B, we're going to do some substitutions using the fundamental identities. So we know the cotangent of x is equal to the cosine of x over the sine of x, and that's multiplied by the sine of x. So we can put a 1 underneath there. So that's equal to the cosine of x times the sine of x in the numerator, and then sine of x times 1, which is sine of x, in the denominator. So we can cancel the sine of x, and we're left with just the cosine of x. So this simplifies to the cosine of x over 1, which is just the cosine of x. So basically, we're just performing some substitutions and then canceling what we can. So this example says simplify the trig quotient, so these are quotients, to a single trig function, no fractions again. So we're going to perform some substitutions first, and then we'll simplify those. So we can rewrite this as the secant of x divided by the cosecant of x. So the secant of x we know is 1 over the cosine of x, and the cosecant of x is 1 over the sine of x. So these are fractions, and when we divide fractions, we change the division symbol to multiplication and take the reciprocal of the second fraction. So now we can multiply. So in the numerator, we'll have 1 times the sine of x, which is the sine of x, and 1 times the cosine of x in the denominator, which is the cosine of x. So we know that is the tangent of x. So this would be our simplified form, a single trig function, no fractions. In part B, we have a quotient again, so we're going to rewrite it as a division problem, tangent of x divided by the cotangent of x. And then we're going to substitute for the tangent of x, the sine of x over the cosine of x, divided by, substituting for the cotangent of x, we have the cosine of x over the sine of x. Now we have the sine of x divided by the cosine of x. If I flip and multiply, I've got the sine of x divided by the cosine of x. So in the numerator, I've got the sine of x times the sine of x, so that's the sine squared of x. In the denominator, I have the cosine of x times the cosine of x, which is the cosine squared of x. So that's equal to the tangent squared of x. So we've written it in terms of one trig function and no fractions. So looking at example 3, it says simplify to a single trig function, no fractions again, but this time we have a little bit more complicated of an expression. So let's rewrite it. So we've got the secant of x minus the cosine of x, and all of that will be divided by the sine of x. So let's work on simplifying this part a little here. So the secant of x we can write as 1 over the cosine of x. And then we've got the cosine of x. If we put that in numerator over denominator form like that, we've got the cosine of x over 1. And all this is now still divided by the sine of x. So our strategy here is going to be to combine these two into one fraction and then divide by the sine of x. And the reason we want to do that is so that we can try to cancel out the sine of x here. So if I want to find a common denominator, I need it to be the cosine of x. So I'm going to multiply cosine of x over cosine of x, which is a form of 1, so that's a legal operation. That way, I'll have a cosine of x in the denominator here, and I'll have 1 here. So then I can combine my numerators. So I can rewrite that, my numerator, as 1 minus, right here I have cosine times cosine, that's cosine squared of x, all over my common denominator, which is the cosine of x. All right, so now this piece looks like this, and I'm still dividing by the sine of x. Right, now I want to look at the numerator right here, and I want to recognize that I have a form of one of the Pythagorean identities. So let me go back to that slide. So likely, when you have a 1 and either one of these two functions together, you can employ some kind of substitution that we can get by rearranging these terms. So I wrote the Pythagorean identity over here as an aside, and I wanted to rearrange those terms so I can perform a substitution and get rid of this minus sign here so I can do some canceling. So these are strategies that we develop as we get the hang of doing these things. So I want it to be 1 minus the cosine squared, and I can get that by subtracting the cosine squared from both sides over here. So I can rearrange these things if I need to get them in a substitution form. All right, so that takes it off of the left-hand side and moves it over to the right-hand side. So now I can see wherever I've got that, I can replace it with the equivalent, sine squared of x. And that's what I'm going to do. So on the top, I'm doing a substitution. Now I have sine squared of x over the cosine of x divided by the sine of x. All right, so I'm going to put a 1 in the denominator so that I can flip and multiply here. So this one stays the same, but I'm going to change the sign to multiplication, and I'm going to flip my second fraction. So now in the numerator, I've got the sine squared of x. In the denominator, let me just put it in left-right order instead, commutative property, of course. So I can see this is the same thing, so I'm just doing a few extra steps here so you can see what I'm doing. This is the same thing as sine times sine on the top, which is sine squared, and sine times cosine on the bottom. That way you can see my cancellation a little better until we get used to doing this. So I could cancel those two out. And now I'm left with sine of x over the cosine of x, and we know that's the tangent of x. Okay, so we've simplified the original expression into a single trig function. So what you want to make sure you're doing here is writing down all these steps. After a while, you get to the point where you could potentially eliminate this step because you can do the cancellation here and, a few other things. But in order to show your work on a problem like this, you would need to be very clear of all of these substitutions and steps and rewriting of the Pythagorean identity that you perform to get all the way down to the end here. So make sure you're taking good notes on these example problems. So example 4 says simplify the expression to a single trig function without fractions again. So once again, we've got a slightly more complicated expression. And our strategies for these, our tools in our tool chest at this point are substitution using trig identities, rearranging it and flip and multiply, that sort of thing. And then the last thing would be performing cancellations and final substitutions. So when I see something like this, I want to write it like secant of x minus 1 divided by 1 minus the cosine of x. And then I'm going to perform some substitutions where I can. So secant of x is the same thing as 1 over the cosine of x. So right now, I'm just rewriting it. Alright, so here, I've got a fraction, and I want to combine this by multiplying by my common denominator, cosine of x, which is a form of 1. So I can combine this whole thing into only one fraction. Alright? So now I've got 1 minus the cosine of x as my numerator over the common denominator, cosine of x. And so I've got that into one fraction now. So I've got this fraction divided by, so if we put a 1 under this one over here, that is also a fraction now. Okay, let's flip and multiply at this point. So multiply, flip. Alright, so this is a binomial expression here and a binomial expression here. So put parentheses around those so you don't lose any of your terms. Alright, so my numerator is 1 times 1 minus the cosine of x. So that's 1 minus the cosine of x. Once again, I'm going to put parentheses around that so I don't mix up my terms. And then in the denominator, I got the cosine of x times this binomial here. And I'm not going to distribute because I can see that those binomials are going to cancel out. Alright, so if I cancel out these matching binomials here, that leaves me a 1 on the top. So I've got 1 over the cosine of x. And I know that 1 over the cosine of x is simply the secant of x. So I've got it down to my final form there, no fraction, single trig function. So some of you might find that these are actually kind of fun to do. They're almost like little puzzles. So these are, I think they're kind of fun. All right, so let's try a couple more here. So this one says simplify the expression, and we've got an a and a b, to a single squared trig function, no fractions again. So it's telling us we're going to have a square in our trig function at the end. All right, so you can see then, here's this piece of the Pythagorean identity again, and we want to do a substitution. So let's just go over how we did that the last time. We started out with sine squared of x plus the cosine squared of x is equal to 1. And then if I want it to look like 1 minus the cosine squared of x, that means I want to move the cosine squared of x over here to be with the 1. Alright, so then I've got the sine squared of x is equal to 1 minus the cosine squared of x. So that means wherever I have this showing up, I could then go ahead and substitute this because they're equal. So that's what I'm going to do. I'm going to substitute first. I'm going to say this is the sine squared of x divided by the tangent squared of x. All right, now I can write it as the sine squared of x divided by the tangent squared of x. And I could say that's equal to the sine squared of x divided by, performing a substitution for the tangent squared of x, the sine squared of x over the cosine squared of x, which is equal to the tangent squared of x. All right, so I've got two fractions if I put a 1 under this one. So I can say sine squared of x over 1 and flip and multiply. So flipping the second fraction, I have this. So in the numerator now I've got this, I've got the sine squared of x times the cosine squared of x in the numerator, and 1 times the sine squared of x in the denominator. So I can cancel out the matching sine squared of x in the numerator and the denominator. So I'm left with cosine squared of x over 1. So you may get to the point where you don't write the 1 anymore. That's just equal to the cosine squared of x. So we've rewritten this as a single squared trig function, no fractions. Now for part B. So part B, in the numerator, if we look at our Pythagorean identity, right here, I've got sine squared of x plus the cosine squared of x. I've got this whole thing, which is equal to 1. So wherever I have this whole thing, I can substitute a 1. So I can say 1 over the tangent squared of x. All right, so there's several ways you can see this. You might be able to see that this is simply the cotangent squared of x, because the cotangent is the reciprocal of the tangent. So that's one path you could take. Another path would be to say this is 1 divided by the tangent squared of x, and that's the same thing as 1 over 1 divided by the sine squared of x divided by the cosine squared of x, which is the same thing as 1 over 1 times the cosine squared of x divided by the sine squared of x, and that's equal to the cosine squared of x over the sine squared of x, and that's equal to the cotangent squared of x. So either path you take, you get to the same place. And that's how it is for a lot of these simplifications of trig expressions, is there's not only one way to do it. As long as you don't take an illegal move, and every move you make leads to the next one in a logical fashion, many times there's multiple paths you can take to get to the same result. So the last example we're going to do here is simplifying a quadratic expression, which is in terms of trig functions. So we think about these like we do a quadratic expression that would have the same coefficients. So that would look like 3x squared minus 5x minus 2. So the way we factor something like that is we multiply a and c together, which gives you negative 6. We factor 6, 1 times 6, 2 times 3, and we choose the pair of factors that adds to give you your middle coefficient, negative 5. So we need to put a negative on one of the numbers, so they multiply to give negative 6. So I'm going to put a negative on 6. These two numbers will add to give me negative 5. So I'm going to replace my middle term with those two instead. So I've got negative 6x plus 1x in the middle instead of negative 5x, and then my last term is negative 2. So now I'm going to do GCF factoring by parts. 3x times x minus 2 plus factoring out a 1, x minus 2. So I should check my distributing here. 3x times x, yes. 3x times negative 2, yes. 1 times x, yes. 1 times negative 2, yes. So now my final factored form is x minus 2 times 3x plus 1. And this is something you guys should be pretty good at by now. So that's how you would factor a quadratic in terms of x. And we're going to do it the same way for a quadratic in terms of a trig function. So first of all, this is your analogous to x squared, sine squared of x. And this here sine of x to the first power is analogous to x to the first power. So you can't have a mixture. For instance, you wouldn't want to have sine squared and then cosine. They have to be the same trig function here. Just like this is an x and not an x and a y, for instance. So I'm going to do it the same way. I'm going to say 3 sine squared of x. Oops. And then my two middle terms I'm going to say are minus 6 times the sine of x plus 1 times the sine of x minus 2. And then I'm going to split it into parts. My GCF for the first two terms is 3 times the sine of x. So I have sine of x minus 2. And I check my distributing. 3 sine of x times the sine of x is 3 sine squared of x. 3 sine of x times negative 2 is negative 6 sine of x. So bring down my plus, factor out a 1. I'm left with sine of x minus 2. These two should be identical. And this sine always comes down to the next level. Alright, so now I've got sine of x minus 2 times 3 sine of x plus 1. So this is our final factored form. So we factor these by parts just like we do with a quadratic. So the reason we're learning these techniques that we've gone through in this section is because these are going to be employed for proving trig identities and for solving trig equations, which have more interesting setups than we've done in the past. Alright, so I hope you took good notes, and we're going to go ahead and attempt the homework section for 3.1, and let me know if you have any problems or questions.